Thank you for the kind introduction. I'm Zhiyuan from Washington University in St. Louis. And today I'm going to present one of our recent work named XCheck. So in this work, we aim to verify the integrity of 3D printed medical devices by leveraging medical computing tomography. So in recent days, 3D printing has seen increasing application in the field of medicine, from regenerative tissue engineering, prosthetics, to organs on chips used for biomedical research. Medical printing is now being used in the real world to manufacture life-saving medical devices. So how does this revolutionary technology work? So first, the patient or the tissue will be scanned to obtain its digital representation. And then they will be sent to medical practitioners for design and customization. Those designs will be sent for manufacturing, and the printed objects will go through a series of post-processing to obtain the ultimate printed object. The key point of this entire process lies in that the designs and the prints need to be customized for each patient to ensure clinical match. However, the security threats in the 3D printing pipeline can lead to severe consequences in this context. Existing work has demonstrated cyber-physical threats in various forms. For instance, the attackers can control the controller PC or the firmware such that they can alter the STL file or materials, and therefore they can achieve malicious prints. As a result, such unique threats have motivated us to develop an effective defense to protect medical printing process. To demonstrate the real-world threats, we also developed our proof-of-concept attack on medical printing. We targeted the FDM printing technology, which has been the focus of existing defenses. And in this attack, we misused the temperature control to cause malfunction of materials solidation. This attack is stealthy because it does not change the nozzle trajectory, which is actually commonly used in existing defenses for monitoring and defenses. And in recognition of these threats in 3D printing, there have been existing efforts developing various defenses. And the majority of them actually focus on the so-called procedure-based approaches. For instance, they will take digital photos of printed processes for monitoring, and some other works also leverage other side channel signals such as vibration and magnet. All of these defenses have shown very impressive performance in monitoring and protecting printing processes. However, we observed some unique challenges in medical printing. We summarize our observations into 4 main challenges. The first is that the medical printing technology is diverse, which is beyond just FDM, which has been extensively studied in existing literature. And secondly, the printing process is even more complicated, and therefore it becomes challenging for us to monitor every single manufacture process. And thirdly, the medical devices are designed to be patient-specific, and therefore it is hard to rely on prior data. And lastly, after communication with medical practitioners, we found that it is generally less interpretable for them to interpret the security analysis results, since they possess less familiarity in security. So to solve these challenges, we propose XCheck as a product-based defense. The key idea is that we check the final product against its digital design. And to do that, we first reconstruct its digital representation from the physical object by leveraging medical CT scanning. And then we validate both the geometry and material aspects of these prints. And lastly, to enhance the usability, we also introduce adjustable and customizable visualization to highlight the potential malicious areas. And we also introduce quantification scores that measures the risks. To summarize, XCheck takes a defense in-depth approach. So to validate the geometry, we first register the CT scans and the design models. And then we develop computational graphic techniques to compare them to reveal these discrepancies. To validate the material, we leverage the attribute value distribution analysis. And at last, we draw inspiration from medical domain gamma analysis to derive the risk quantification. So more specifically, there are two key techniques for detecting geometry attacks. First, we developed the voxel analysis. We first voxelize both the CT scans and design models and compare them to compute the Hausdorff distances. We also derived theoretical security analysis, which shows that this algorithm can actually reveal any modification that is larger than twice of the CT resolution. We also developed ray-based analysis that is designed to defend against the adaptive attacker. And by using rays intersecting with both models, we can capture tiny discrepancies. The intuition behind the material validation is that various materials actually exhibit different X-ray absorption characteristics. Such characteristics or features are reflected in attribute values. However, we also observe that those values can be affected by geometry as well. Therefore, we choose to study the attribute value distribution. The figure here shows that the results of the bond screws printed with different materials. We observe that those printed with benign materials will cluster into a group, while those printed with other materials actually diverge significantly from that cluster. And lastly, to enhance usability, we developed both interactive visualization and the quantitative scores that actually aggregate various monitoring factors such as scaling, geometry deviation, material discrepancies, etc. And just like existing work in 3D printing defenses, we have to develop our own models and attacks. We work with medical practitioners to design base models and also develop 11 realistic and stealthy attacks that can compromise device functionalities. So in total, we printed 47 devices across 4 applications and 7 materials. And our results show that XCheck can achieve high detection rate with relatively low false positives and false negatives, which are also equally important in the context of medical printing. So in summary, we develop a defense in-depth approach to provide multi-layer protection for medical printing and to enhance the usability to help the medical practitioners. We develop adjustable and customizable visualization and the risk quantification. And we are very honored to be awarded with Distinguished Artifact, and we have open sourced our models and source code for the community. That's all for my presentation today. Thank you.